In this video, we are going to discuss derivatives and rates of change, specifically how a rate of change is related to the derivative, which we will finally formally define. Our learning objectives are fairly straightforward and also tied into some of the things that we have done before. First, know and understand the definition of, wow, typed that wrong. Know and understand the definition of the derivative. Sorry. Understand that the slope of a line, rate of change, and velocity are all the same thing. They're the same types of problems, the same interpretation. And third, we will have to calculate derivatives as the limit of the difference quotient. We'll see what that is in a bit. You can see at the bottom a lot of the vocabulary that we are going to use throughout this unit, throughout this section. So first of all, how do you calculate slope? Well, at its most basic level, rise over run. But rise over run we had noted as like y2 minus y1 over x2 minus x1. But instead of using x's and y's with calculus, we tend to use more advanced notation than just in an algebra class. We were noting it's the function value and the function value over the two pieces. But even beyond that, we're not just using x1 and x2. With this particular drawing, we would have our point P and the point Q, noting that P and Q are the heights. And that's just over, I have that backward from the way the drawing is put. This one is drawn Q minus P, X minus A. But still, it's the same idea of slope, everything that we've done. The key feature behind this is we have our two x values, and the distance between them can be described as x minus a. We have our rise, which is f of x minus f of a. How could you use that to create the equation of a line? Remember, equation of a line in point-slope form was this. If we calculate the slope using the slope formula, we could pick a point like a f of a or x f of x, but we could pick a point and just start plugging them in like y minus the y height f of a. Then we'd have that slope we calculated, x minus a. In our previous work, we'd seen a lot of these pieces where we were creating the equation of a line, but we had to do some work to figure out the slope. What would happen if we started dragging this number a closer and closer to x? So instead of being this far away, what if I was using an a value that was there? But when we come up, that would put point P here, which would shrink the rise and it would shrink the run. Drag it even closer still. Come straight up, and it's getting shrunk even more. Come even more close. You can see that this size of this triangle up at the top is getting really tiny, so small that I can't even see it on this anymore. Bring it closer and closer and closer, clearly hinting at the idea of a limit. What is happening to the slope when we're going, there was blue slope, there was yellow slope, and here is purple slope. What's happening to the line? In particular, this is becoming a tangent line. The closer we get, it gets closer and closer and closer from being a secant crossing at 2 into becoming a tangent at 1. Well, of course, I'm hoping you recognize this idea of becoming closer and closer and closer means take a limit. If you take the limit of a secant line, you will get the tangent, at least in regard to slope. That's exactly what this stuff is. This whole piece that's sitting here showing you, here was the original. You can see they're taking this point Q and dragging the A value closer and closer and closer, and you can see how the slope is changing on the right-hand side. We have this definition. The slope of a tangent line is the limit of the slope formula. Slope formula, f of x minus f of a, that's our rise. X minus a is the run. And we're just going to take the limit, dragging the a closer and closer and closer until we get tangent. Intuitively make sense? Now, because it's a limit, will the limit exist? The limit might not exist. Slope might be a vertical line. And if we have a vertical slope, then there is no slope. That's going to mean no slope, so we'd run into problems like that with a tangent doesn't, where the limit doesn't exist. That would be an infinite limit. An alternative way that this is frequently characterized, instead of saying take A and drag it closer to X, we would use, instead of X, we would call A plus H. You see that it's still the same idea? We have this distance, and we have a distance. It's just different ways of characterizing the distance. But the idea is still the same. Shrink the horizontal distance to change it from a secant line, and limit on to become a tangent line. It's just a different way of writing the limit. On the left, we would say the limit is taking x approaching a, but on the right, the distance between x and a, which we call h, is shrinking down to be nothing. But the ideas are still the same. You can see the pictures are absolutely identical. It's just it's doing a change of variables, a different way of describing the picture. But the picture is the same, the understanding is the same. Also noting that part, look familiar from a previous course? It should. In your previous classes, this is a piece that you would have worked on with the difference quotient. If you take the limit of the difference quotient as h approaches 0, you can get the slope of a tangent line. We'll actually come back to this in just a second. So here's our first part. Find the equation of the tangent line to the parabola y equals x squared at the point 2, 4. Okay, so find the equation of a line tells us we have this. If you haven't memorized it before now, might be beneficial because we use it a lot, don't we? Well, we already have the x1 and the y1. The only piece that's missing is slope. But we know slope of a tangent line is going to be this limit as x approaches a. Well, our a value is the x value of 2. And we need f of x minus f of 2 over x minus 2. What is f of x? What's the function? It's x squared. So this is a piece that we could say x squared. What is f of 2? Just plug it in. 2 squared is 4. So that piece becomes 4. And we have to evaluate this limit. That's the major thing that we need. Instead of using the tables, instead of using the graph to try to figure out slope, we can just do a one limit and get slope. So how do we do this limit? No, we could use the difference of squares formula to split up the numerator into x plus 2, x minus 2. Yeah, those will cancel, giving us limit x approaches 2 of x plus 2. Direct substitution helps us out here. Our limit's 4. There we go. We're now done. The limit is slope. That was the whole point to this first part. The limit of the difference quotient, whether you're writing the difference quotient as f of a plus h or this f of x minus f of a, this part, if you take the limit, that is slope of the tangent line. That is one of the critical things to understand about this beginning part. Limit of the difference quotient is slope of the tangent line. I cannot emphasize that heavily enough. If I could, I would have streamers and balloons flying around so that you would know this is critical. You are screwed if you don't understand that. Obviously, it's not like if you're screwed if you don't understand it right now, but you do need to learn that component. For this problem, I use the format of f of x minus f of a over x minus a. I use this format to do it. You have your choice, though. You can choose to use this format, or you can use the other one where you take h approaches 0 and use this one. I strongly recommend you write both down, you memorize both, because they're both very handy. The big reason that we'd use these as a strategy is that depending on the problem, sometimes the algebra is easier with the first definition. Sometimes the algebra is easier for the second definition. So when you're trying to work through one and you get stuck where you can't figure out the algebra part with simplifying, a lot of times if you just use the other one, it'll be easier. It depends on what the function is. So let's use this one. Find an equation of the tangent line to the hyperbola y equals 10 over x at the point 5, 2. Now, once again, we have y, I want to switch this to black, y minus, I said black, give me a black pen please, y minus y1 equals slope x minus x1, but we already know x and 1, y1, that's y minus 2, x minus 5, and all we need is the slope. But the stuff in yellow will give us the slope. So let's start crunching through, and this is where I'll use some red. We would have f of a plus h minus f of a over h. Well, let's start replacing pieces. What is f of a plus h? That's 10 over a plus h. Just replace the x with that. F of a is just 1 or 10 over a. Now, we need to do some algebra that will allow us to simplify the numerator. Well, we have fractions. If you want to add or subtract fractions, you got to get a common denominator. So we would need a plus h on the right. We would need an a on the left, which would allow us to rewrite this as 10a. I started writing a plus sign, but it's minus 10 a plus h all over a plus h all over h. You see the distribution that we could do on the numerator? If we distributed across, we would obtain, switching it to yellow, minus 10a minus 10h. Why is that beneficial? Because we can now cancel, which would allow us to rewrite that whole piece now as negative 10h over a plus h all over h, which we could write as h over 1. Multiply by that reciprocal, multiply by the reciprocal. It cancels, simplifies, so we'd have negative 10h over h times a plus h. And we get some more stuff that cancels, which would then give us negative 10 over a plus h. I intentionally left the a in for a while to show that we could do all this with the a. We actually do have a specific a value, though. The a value is our x value. That was 5. So at this point, I want to plug in a equals 5 just so that we can have some specific numbers to look at. Whoa, I went down a little bit further than I intended. But that would give us negative 10 over 5 plus h, which would simplify to negative 2 over 5 plus h. The h did not go away. It's still going to be there. This part in the end, this is the difference quotient. But slope, going back up to the original yellow, is the limit of the difference quotient. If we take this piece and now come down and say the limit as h approaches 0 all the way at the end of this piece, we will get our slope. All that stuff up ahead was just algebra. A lot of algebra, but it wasn't calculus. It was just algebra. So, of course, there's reasons why you had to take algebra classes. This is our calculus step. Do this limit. I'll plug in h is 0. We get negative 2 over 5. This part in purple is calculus. All the stuff above it was algebra. So there we go. We're done. Calculus is purple. The calculus part actually isn't that bad in comparison to the rest of the problem, right? Now, the history of calculus, if you look through back when it was invented a couple hundred years ago, or I should say discovered, I don't know if invented is the right word, but when calculus was being developed, one of the motivating forces was trying to explain how things move. In particular, how do the planets move? Well, we're not going to get into that level of complexity. We would need a lot more advanced calculus than we will develop. But it does give us one of the fundamental ideas, that of a position function. We are going to use functions to describe how functions move, or how things move over time. For example, if this is my time of 0, and I start considering how it moves to become a time of 1, and continue it forward to be a time of 2, and I'm using this as equal spacings, time equals 3, time equals 4, time equals 5, time equals 6. So basically we're just mapping this out. Oh, didn't need that. Needed it there to go back. If we were saying this is not a number line that's evenly spaced, but how a thing is moving along a line, where is it moving the fastest? Well, this is a long distance over a time of 1. Where is it moving the slowest? A very short distance over the same time interval. Now, we don't have equations mapped with this, but what we would like to be able to do is to create a relationship between where things are located and another equation that says, here's my speed. Here's how fast things are going given the position. How fast the position is changing is velocity. Velocity, as we were doing back in our previous work with the velocity and tangent problems, velocity is nothing more than slope. You ever see a piece that says velocity? It's a slope problem. Average velocity is slope of a secant line. Instantaneous velocity is slope of the tangent line. It's just looking at, are we considering speed, or velocity, over a time interval of 1, which would be average velocity? Or are we saying a time interval of right now, at this exact instant? And we know to get the instantaneous, we would take a limit of the secant. So here we go. A ball is dropped from the Empire State Building roof, which is 443 meters above the ground. How fast is the ball going at 5 seconds? How fast is the ball traveling when it hits the ground? Well, two very similar problems. The algebra is going to be the tougher part to this one, like a lot of things. What is the velocity of the ball? Well, remember, velocity, we could use distance is equal to rate multiplied by time in general. And so velocity we are considering is rate is distance over time. Well, our position function is 4.9 t squared. What we're looking at doing is saying I have 4.9. Trying to think of a better way of phrasing this. If we want to know velocity, velocity is slope. So we are looking at slope of the tangent line. Once again, this is a piece that we could take the limit, and for this one I'm going to choose to use x is approaching 5 and use f of x minus f of 5 over x minus 5. If we can figure out that, we have our instantaneous velocity at 5 seconds. So f of x, what is our position? What's our function? 4.9 t squared. Well, perhaps I should actually, since we're using this variable t, I should actually call this t is approaching 5, so that way the letters are matching. But we'd have 4.9 t squared, and then f of 5. 5 squared is 25, so what's 4.9 times 25? $122.5. I've chosen to write it out this way so that we can actually see some pieces. I'm going to ignore the limit for now and just note we could factor out a 4.9 from the numerator, which leaves behind t squared minus 5 squared. Why would I want to leave it that way? So we could see that as a difference of squares, this is a piece that would factor as t minus 5, t plus 5. You see it? Yes, I should. I did not do that one yet. Thank you for pointing out, Scotty. I needed to switch that to a t as well. That way my variables are matching up. But then I've got t minus 5 in the denominator. Those cancel. And so our limit then is saying take the limit as t approaches 5 of 4.9 t plus 5. We'll just direct substitution. 5 plus 5 is 10. 10 times 4.9. We'd have 49 meters per second. That's how fast it's falling at that exact instant moment in time of 5 seconds. I'm going to erase all this stuff to give me some room to work. But then we will note, how fast is it falling when it hits the ground? Well, here's our big part. It's going to be pretty similar, but this is the piece where we knew in part A we're doing time of 5 seconds. Do we know how long it takes for it to hit the ground? Well, we could use it though, because we have 4.9 t squared has to be equal to this height of 443. So solve the equation. 443 divided by 4.9, and then take the square root of that. Students are currently working with their calculators to save me a bit of time. I appreciate that. But we'd get our result, 9.5. Is it exactly 9.5? 9.5 what? Okay, 9.508. And that's rounded to the nearest thousandth place. It does go further. And so our value here is going to be a little bit off. If we wanted to, we would actually need to use t is equal to 443 over 4.9 and use that for our piece. Our a value, instead of using a of 5, this would need to be our a value. We're just going to use this 9.5 approximation to increase the simplicity. But now that we know our time value, it's the exact same problem as A. How fast is it going? We just know how long it's going to take to hit the ground now. So we would still have the same limit of t approaching 9.508, f of x over f of a over x minus a, but all of that turned out to be, when we simplified it, 4.9 t plus, and before it was 5. I'm seeing some confused looks, so I want to backtrack and look at the problem again. So we'd have f of x minus f of a over x minus a. X, I need to use that letter t again. F of t and t minus a. Well, f of t we know is 4.9 t squared. F of a, what's the height when it hits the ground? 0. So this would be a piece that we would have a height of 0, and our a is, back up, we'd have 4.9 t squared minus 0, but the a value was this other x1 that we were approaching. Well, when we start simplifying these pieces, bang. One of the pieces that I just noted where I was having a brain fart and my mouth wasn't matching my brain and blah, blah, blah. But this f of 9.508, the f of a value, that was the height, or how far it's fallen, which we knew was 443. Essentially, when we're taking this piece not with 0, but at 443, we are noting the 443 over all those pieces stems from the same piece that we had here. This is a piece that we would be able to have rewritten with our f of a value for 4.9 times 9.508 squared. Because we still have the same 4.9, we could factor out the 4.9, which would give us t squared minus 9.508 squared. I have that squared written in the wrong spot. Well, when we start doing our simplification like we had done previously, t minus 9.508, it's not 9.508, it's the 400, dang it. Man, I cannot get a break, and I'm just absolutely foolish with the writing. I'm sorry, just my brain was dumb and I was making some mistakes. This part right here was the 443 over the 4.9, which was how we wound up getting our 9.508. The square root is that part, so when we wind up splitting these pieces, we would have our factored form 4.9 t minus 9.508 t plus 9.508 over t minus 9.508. They still cancel, and what we wind up with is this form of 4.9 t plus 9.508 and then we're taking the time, the limit, as t is approaching that. So we'll plug it in. 9.508 times 2 times 4.9. $93.178 meters per second, and that's what we wind up with. Yeah. Sorry for the messed up with the algebra. I'll try to be more clear. 93 meters per second. 93 meters is a little bit less than a football field. So run the whole length of a football field in 1 second. That's about how fast it would be going. A little bit slower than that. Critically important, pause the video. I already had it going a little bit, but here are some things to note. The derivative. Please keep in mind that the first whole part is called differential calculus, which is derivative calculus. The derivative is the slope of a tangent line. The derivative is the instantaneous rate of change. And if we're talking rate of change in position, that's velocity. And it is the limit of the difference quotient. 3 synonymous things. You should know the derivative is all of them. Critically important for you to know these pieces because this is the foundation behind pretty much all the interpretation problems. This is the foundation behind why we care about calculus at all. So, find the derivative. Finding the derivative is no different than saying find the limit of the difference quotient. Find the slope. That's our f of x minus f of a over x minus a. So we can start plugging pieces in. I wrote that. Hang on. X. I was combining the two forms for a second. X. I don't want red. I wanted blue. X approaches a. Hang on. Let me write it out this way as well. Limit h approaches 0. F of a plus h minus f of a all over h. We have the two different forms. Choose which one you want to use. The left or the right. We don't have enough time to do both. Show of hands for the left one. Show of hands for the right one. Okay, so if we're doing the right one, we would have the limit as h approaches 0, f of a plus h. So that's a plus h squared plus 2a plus h minus 3. Minus, and we're going to minus each individual piece, minus a squared minus 2a minus a negative 3 becomes plus 3 all over h. All right, a plus h squared, a plus h quantity squared, a squared plus 2ah plus h squared, distributing, we have 2a plus 2h minus 3 minus a squared minus 2a plus 3. Yeah, now we've got a lot of stuff that we can start canceling. H approaches 0. All right, so let's look for stuff that cancels. A squared, 2a, and the 3's. Okay. Bryant said, and the h. You're correct, sir, the h will, but before we do that, I would like to factor out the h from the numerator and see what's left. That would be 2a, took out an h, plus h, plus 2, all over h, which cancels. And now when we evaluate the limit as h approaches 0, 2a plus 2. That is our derivative. The reason why this is so cool is because this is the slope for any point x. If you want the slope at at x equals 5, just replace a with 5 and you got your answer. If you want the slope when x is 50, replace a with 50, you have your answer. We don't have to do a separate problem for every single one of them. We can do this whole process one time and then just replace a number and get the slope for anywhere. Yes, slope of the tangent line. Find the equation for a tangent line to the parabola y equals x squared plus 2x minus 3 at the point 3, 0, negative 3, 0. Yes, this is what we were doing before, but specifically, since we're looking for slope of a tangent line, let's take our limit, h approaches 0, of, well, the whole point that we're noting, I'm hoping that you guys saw, it's the same function. So from what we were just doing, going back to example 4, it is the same function that we just did. So we already have our derivative. The derivative was 2a plus 2. Well, what is our a value for this particular one? A is negative 3, so if we plug in negative 3, we can get our slope. 2 times negative 3, negative 6 plus 2, that's our slope. And isn't that a whole lot easier than doing all the graph and the table, and it's a nice little piece. If you can do the limit of the difference quotient, we can then start figuring out a lot of other values a lot quicker. Especially when you think about the homework where we had like part A, part B, part C, and you had to do it 6 times. Wouldn't you rather do this 6 times and the other stuff once? That's where this becomes really beneficial, is when you need to do a lot of them repeated. Now, y minus y1 equals slope x minus x1. Voila, we're done. Rate of change, and I've emphasized this, I've said it. Rate of change is a measurement of how fast a function is changing. In a position function, rate of change is called velocity. If it's not a position function, we'll just say rate of change, but the ideas are absolutely identical. Rate of change, velocity, it's slope. Slope of a secant line, you take the tangent, you get the slope of the take the limit for the slope of a secant line, and you get the slope of the tangent line. Average rate of change, slope of a secant line. Instantaneous rate of change is the tangent line. So it's still slope, 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 slope. And I want to point this out. Slope of a tangent line is our derivative. So a manufacturer produces rolls of foundation sealant that always have a fixed width. Typically, they go 4 feet wide in the US. The cost of producing X yards of the sealant has a fixed cost, C equals f of x. What is the meaning of the derivative? There is a notation here that I have not yet presented to you. F prime of x means the derivative of x. You know how we had the 2a plus 2? That would have been our f of x. 2x plus 2 was the derivative of what we did before. But we don't have a function. So this whole thing is, what is the meaning of the derivative? Well, remember how we were talking position function and velocity? If you take the derivative that's what we're noting. It will tell you how fast is the cost changing. For example, if you are going to create 1 roll of sealant, is it expensive to create 1? Or is it basically, if you're going to do this whole production cost, buy machinery, buy the stuff, hire employees to create one role, is the one role really, really expensive? Well, yeah, you have to pay for the machinery. You have to hire employees. You have to pay taxes. It's really expensive to do one role. But if you made 20 roles, do you have to pay the 20 times over to get the machinery? No. If we took the derivative of our cost function, it will tell us how fast the price or the cost is changing. There will be a time when it's cheap to make a certain number of rolls. There will be a time that is expensive to make a number of rolls. We're actually going to discuss this a little bit more on the next page. I'll try to elaborate further. But the units is the cost function per unit. How many of you have taken Reimer's classes like accounting? Do you remember doing marginal cost? Okay. Well, that kind of blew my whole thing out of the water. Welcome to marginal cost. Instead of the price to make 500, what is the price per one? In part, it's like doing a unit rate. So, in practical terms, what does f prime of 50 equal 14 means?
All the students need to come down here, Rebecca Wells, Monica LaPlante, and Brooke Howe, also Clint Abel. The following students are going to be in ICU over noon, and we're working through the beginnings of the camp. So it's Eva Guru, Jalen Goodiron, and Cody.
So here we go. F prime of 50 is saying to make the 50th roll, it's going to cost us $14 more. If we had something that was f prime of 1 equals 300, to make the first roll, it costs us 300. Of course, the idea behind that is here. Is it going to cost more to make the 50th roll or the 500th roll? Well, think about if you have to go buy a boatload of machinery and you're only going to make 50, are you really making a lot? No. So there is very high upfront costs. Because there is a lot of upfront costs, the price of making 50 of them is going to be pretty expensive. But if you start getting into a point where you're getting in a rhythm and your people get really good at it and they're efficient, is it going to cost you as much to make the 500th roll? No, because your employees are going to be good at it by then. They'll know what they're doing. It's the idea behind the assembly line. If you are doing an assembly line, it's slow at first, but once people learn their job, they can knock it out really quick and really fast. That brings the cost down. We would expect the price for the 50th roll to be more than the cost for the 500th. But what about doing 5,000? All of a sudden, with 5,000, you're now looking at a point where you're not a small store anymore. If you're going to be doing 5,000, you're going to need more employees. Or you're going to be paying overtime. You're going to have machines that break. And when the machines break, you have to get them fixed. So there are additional costs with doing a large-scale operation. Being really big is going to drag the price back up above what it was for 500. Maybe to the point of being 50, maybe less. It depends on what the function would actually turn out to be. But that's the basic form for where we'd be looking. And here's our last one. D of t is the U.S. debt at the U.S. national debt at time t. The table gives us some approximate values of the function by providing year-end estimates from 1980 to 2005, but it's not complete. Interpret and estimate the value of d prime 1990. The interpretation we can do pretty quickly. in 1990, the national debt, the speed at which the national debt is going up was blank. We don't know the number. We will actually have to figure out a function. We're going to do a linear modeling with our calculator, get a regression model, and with the regression model, we could then do the derivative. With the derivative, we'd be able to get our answer. Now, I would like to reinforce the derivative, which is also the rate of change, which is also slope of the tangent line. Those are all the same thing. If we're looking for the rate of change in this problem, one way to get it is to estimate the slope of the tangent line to the function at the point when our time is 1990. So one option we can use is to go to the calculator and put all our information in a table. After building the table, you'll notice I have the time, and I used 80, 85, 90, understanding that it's 1980, 1985, and at 100, it's actually the year 2000. 1900 plus 100 is 2000. But I've got our table of values from here put in the calculator. From the calculator, I've already set this part up, but you'd have to go to Document, Insert, Data and Statistics. If you inserted Data and Statistics, it would allow you to recreate, change the axes, but lets you create this. The important characteristic that we are trying to note then is at this point, when we have 1990, what is the slope right here? If you were trying to put draw a function to this piece, whoa, did not want that, and I don't know how to back this part up. Anyhow, if we were trying to create and say, what's the slope at this point, we could say, well, from here to here, you'll see the values I have picked. What's the rise? What's the run? This is one where we can see we have 44, 31, 22, 57. Well, 44, 31 up to 22 and 22, 57, we could come right around here and say that's a rise of about 4,200. Keep that in mind. The rise is 4,200. Our run is going from 88 to 93. That's a 5-year run. So we are taking an estimate where the rise was 4,200 and the run was 5 years. That's giving us a total of 840. This is actually, and you'll note the pieces I was using, that was over a 5-year window. This 5-year window is a secant line. A secant line is the average velocity. If we were trying to obtain the instantaneous velocity, we would need a smaller area. You notice this one, how we're going from 89.19 up to 90 point there. Well, we could try to shrink this in on this a little bit more. 89.67 up to 90.02. Well, what's the rise there? The closer we could get in on this piece, and I'm trying to get closer than 89.67. There, 89.9. That's about as good as I'm going to be able to get. Our rise is about 700. It's actually 692. And the run is 0.22. So using a smaller window, we would have 692 over 0.22, and we'll come back to the calculator to do some number crunching there. 692 divided by 0.22 is 3145.45, giving us a much better estimate. Noting that 5-year window was pretty far off when we were considering where we actually were. This is a big reason why when you're using a secant line, you want secant lines that are a lot closer, and fortunately we were able to do an estimate for that. That's not to say that we wouldn't have been able to go through and done other ways, but this is just one way, estimating the slope. Sum up all of this that gets put together. Most important pieces to know: this one page is absolutely huge. The derivative of a function is the slope of a tangent line. It's also the instantaneous range. It is also the limit of the difference quotient. They're three interpretations of the same idea. And this definition, f of a plus h minus f of a over h, the difference quotient, take the limit as h approaches 0 of the difference quotient. I want to emphasize, critically important that you learn this component because it's the major way that we will interpret our work going forward. We know that this is a lot of work to actually do the difference quotient and to take that limit. We will learn a number of shortcuts for being able to get this done more quickly, but no matter what, this interpretation never changes. So, know and understand the definition of a derivative. Understand that the slope of a line, rate of change, velocity are all the same, and be able to calculate a derivative by using the definition. If you're able to do those three things, you should be good progressing forward. Nope, wrong button.